Tonight we're going to talk about the things we have on Mars, in particular Perseverance and Ingenuity, their current status, what's currently happening, and some recent, I won't say new science facts, because in order for it to be a fact, you typically want peer review and who else is currently on the surface of Mars. So it's new data. It's new data waiting to be confirmed. And if you think that that's a little odd, as the space probes went to the outer planets, to Jupiter, Saturn, Uranus, Neptune, they reported finding lots of new satellites, new moons of those planets. So they went into the waiting to be confirmed list. And when a next probe went by and confirmed them, then they would officially be put on the list of natural satellites of those planets. That's why you see jumps in the number of moons of Jupiter and Saturn, is because we had things that went out there. So when the Galileo space probe went past Jupiter, it found a lot of new moons. And then when the Cassini space probe went past Jupiter on its way to Saturn, it was the second confirmation data and therefore confirmed it. So what we've got now is Perseverance has found new information given its observations of Mars. And so what next is going to arrive at Mars to confirm this stuff? Well, we do have orbiters orbiting Mars, but they can't get the high resolution images or atmospheric samples that Perseverance can. And even Curiosity, the other large NASA rover on Mars, has different instruments. So it can't detect all that Perseverance has uncovered. So it'll go into that list of, here's some new data, here's what we think it means, but it's not science yet because we have to get another probe to go there to confirm it. But that's just how science works. But first, the news. So in the category of, look, it's still down there. The Mars Reconnaissance Orbiter was once again stretching out its high resolution cameras and took a picture of Perseverance on Mars. It's the little dot right there. You are here, Perseverance. It's a nice colorful picture with lots of rough stuff. So if you look at when NASA first went to Mars, they went to Utopia Planitia, which is a large, flat sort of desert, which made sense for, we don't know how the ground is going to hold up and how difficult it will be to land there. So we're going to land in some place flat and safe. But by the time you get to Perseverance, oh, well, give us a small flat spot. We can land there. And they say that if you look really closely, like right through here, you can actually see rover tracks where the rover has gone. So anyway, that's Perseverance as seen by the Mars Reconnaissance Orbiter. I'll get into this in more detail during the presentation, but all of the missions in orbit or on the surface of Mars will go into a radio silent mode for the next few weeks. And this is due to the celestial alignment of, from Earth's point of view, Mars will be behind the sun. And as it approaches being behind the sun, we start to lose communication signal from everything around or on Mars. So it's not just us.
In astronomy, the name in astronomy is opposition.
I have no opposition to using that term. So things will go in shutdown. China announced more than a week ago that their rover on Mars was already planning to shut down. So not the first.
Hey, that was a big thing to just get there. And they got at one time a rover, lander, And the orbiter, that is like, wow, incredible feat for one mission.
Yes, I do believe that given all of the times that nations have attempted to do things on Mars and failed miserably, including NASA, a little problem with, is it feet or meters? I can't tell which. Yes, the odds on making it to Mars, getting into orbit, landing, and then successfully deploying a rover all on one mission, kind of on their first try, that was awesome. And in the delayed again news, once again, the Space Launch System, this is the thing that's supposed to take us back to the moon. It was delayed until mid 2021. And now it's, the odds are it's going to be in 2022. No specific word as to why this time. It's just 2022. But it's not officially 2022. We're kind of thinking it's going to be 2022.
Who's the manufacturer?
It's a partnership. It's the SLS, which is not the same as ULA, which is essentially Boeing. This is the Artemis program, us going back to the moon. I don't think SpaceX has anything involved in the Space Launch System, the SLS. Oh, here's something else new. NASA internally reorganized, and they now have 2 moon programs. One is for human-based, and one is for not human-based. I mean, NASA's always had multiple things going on, especially in their works in aeronautical engineering with Jet Propulsion Laboratory and the Air Force. So this is just a further divisional alignment within NASA. If you understand the history of NASA and you know what James Webb did for NASA, this is just a further splintering to make sure that if Congress suddenly decides, we're not going back to the moon anymore with people. Well, what about the non-people things? Oh, that gets killed in the same budget. By splitting it into multiple budgets, should the manned resumption of exploration on the moon not happen, you can still have the unmanned exploration and preparation and gateway and things like that of the moon. So I don't see it as a bad thing.
Oh,
but
the scientists on NASA are not just book smart, they're street smart.
Yes. There are some in the upper administrative levels of NASA that have seen what happens within NASA if you don't pay attention to where the money is coming from. And one of my funniest sounding space probes out there, the BepoColombo. This is the one that takes the long looping approach via several gravitational assists to get to Mercury and take close-up higher technology images of Mercury. So it's actually looped around kind of in the vicinity of Mercury a couple of times, but now it's getting closest to it. So you can start to see better pictures. Now, BepoColombo is a joint venture between Europe, the ESA, European Space Agency, and Japan, JAXA, the Japanese Space Agency. So while there may be some comments that the U.S. is assisting in their efforts, NASA is not really a part of this program. It's really the ESA and JAXA. So if you think the extraterrestrials are looking for Earth, here's good news for you. If you're afraid that they might find us, the Earth is getting less reflective due to climate change. Now, what that means is, as you know from trying to do astronomy with a telescope in an observatory environment, that when you have high humidity in the upper atmosphere, it distorts the light coming down to the Earth and therefore makes imaging difficult. Well, as the Earth heats up, the amount of moisture in the upper atmosphere is being reduced, and therefore it's making the Earth as viewed from deep space, dimmer because there's less reflectivity of light from the sun. So we're going into stealth mode. If you remember the discussion from last week about the ozone hole at the Antarctic, this is kind of related to that because we knew that there was a reduction in the amount of ice particles in the upper atmosphere, and that was likely what's causing the ozone hole over Antarctica to grow during the warmer months. And so this is kind of the same thing. It's less moisture in the upper atmosphere means the Earth's atmosphere is less reflective to deep space, which also means more of the heat makes it down. It's not the CO2 warming blanket, but it is solar radiation that in the absence of reflective moisture, more of it can make it to heat the ground. And in the beginnings of a follow-up to last week, the question was, anybody know anything about ERVs or energy recovery ventilators or heat recovery ventilators, their HRV counterpoint? I started doing some research and found there is a home ventilating institute, HVI, and they've got a consumer pamphlet on it. So I put this in the email, and I'll pop this in the link in the chat window. So if you want to learn more about what's an HRV, what's an ERV, and how are they related to consumers, it's all about there's heat outside, there's heat inside, there's moisture outside, there's moisture inside. And as you move the heat and the moisture from one zone to the next, you can make temperature transition. So this is devices, and the ERV as being more all-encompassing because it not only deals with the heat, it deals with the moisture as well. So transitioning that from the inside and the outside. I look at it and go, well, it's simple physics, and I'm sure that these units might have some technology in them, but given how much they're hyping them, and there's an institution out there waiting to promote the manufacturers of such products, that I'm going to guess you're going to have to pay more for them than they're really going to be returning. It may make your house feel more comfortable, but how much of a percentage of your home air conditioning system is that going to cost you? If you're out in the US Southwest, swamp coolers, if you don't know who to get them from, can cost you as much as an entire air conditioning system, and there's no compressor involved. You know, there's a lot of coils involved. This looks to be the same sort of thing. There's a lot less technology involved and more just simple physics principles. But I would say it doesn't look like a scam, but it looks like a high profit margin business for those already in the business of selling and installing whole house air conditioning and heating systems. It's like, hey, there's some more money on the table. We need to claim that. So.
Okay.
So before you go out and spend a lot of money on it, I'd say read up about it and see what it's actually doing for you.
Yeah.
I mean, Florida has high humidity. Our heat itself is not all that high. You know, we don't get into the over 110 degrees kinds of things, but our heat index is high because we have high humidity. Okay, any other news? All right. Given the recent data findings that Perseverance has found, plus something that happened this week with Ingenuity, plus the alignment of the planets and the sun, I thought I'd just do an update. And it was actually Adam that brought this to my attention. NASA JPL does kind of a day in the life thing for NASA JPL, and they did one on the stuff they got going at Mars, particularly Perseverance and Ingenuity. So I said, oh, there's data there. I can draw from that siphon. without having to do a lot of in-depth research. So that's where all this comes from. So the two things that we'll talk about are Perseverance and Ingenuity. Perseverance is the rover. We've had a number of six-wheeled rovers on Mars, and this is the latest one. A couple of rovers ago, we learned that if you want the rover to last a long time on Mars, solar panels is not good. If you have a thing that you land on Mars, like a lander that doesn't roam around, solar panels are really a pain because Mars has continual dust in the atmosphere that settles on things, even when you're not having a dust storm. But when you're having a dust storm, it can really be a mission ender for your lander. So much like Curiosity, Perseverance is radioisotope thermoelectric generator powered. It's not fission and it's not fusion. It's there's a bunch of plutonium inside of a sealed container, and they run thermocouple wires inside the container, and the radioactivity, the decay of plutonium keeps it nice and warm, about 400 degrees Fahrenheit. And there's no on and off switch. When you start it up on Earth before launch, it starts producing electricity, and there's no stopping it. There's no control rods or anything. So it's going to be producing a reasonable amount of electricity for decades. The Voyager spacecraft, which are out on the edge of the solar system, those are also RTG powered. They are way too far from the sun to get enough energy to keep them operating off of photovoltaics. The farthest we've taken that is the Juno mission around Jupiter, and it has extremely large solar panels to collect up enough photons to convert to electricity to power it. And we did that because we were in short supply of plutonium, because we're not building hydrogen bombs all the time anymore. So there's no surplus of plutonium that NASA can draw upon for deep space probes. Luckily, we resurrected the program on a mild basis. Trust us, we're only doing this for space exploration. We're not making any more big bombs. So we got enough plutonium for the Perseverance rover. And so that's what Perseverance uses for power. Plus the fact that it's a rover means it's probably good until its wheels either get stuck or the ground glass of the soil of Mars, destroys the wheels, which is happening on Curiosity. If you've seen the wheels on Curiosity, there's some wheels of questionable state that may just be spokes in the ground in the not too distant future. So that may be the ultimate end of Curiosity, is it can't tread sand. The helicopter demonstrator, Ingenuity. Yes, it's a helicopter flying on Mars. And they had to do some redesign from helicopters on Earth because Mars has such a thin atmosphere that you need slightly wider blades. You need much longer blades. They need to rotate faster. They need to have a very deeply variable pitch on the tilt of the blades, and all those things went into account. So they were very happy the first time that the helicopter actually lifted off from the surface of Mars. But it was just after coming out of the winter months. The atmosphere was thicker, so it flew. And it flew, lucky 13 times. And then we got into the Martian summertime. Well, there's been a problem, and we'll get to that later. But it uses photovoltaics, and it has limited battery storage because that's how you balance out how high and how far and how fast you can fly versus how heavy the craft is. And you've got solar panels on the top to recharge it when it's not flying. And there's a delicate balance to all of that. And they were successful when the atmosphere was thin, but still thick enough. So it flew to Mars, piggybacked under the belly of Perseverance, and it was dropped to the surface by about 18 inches gap so that Perseverance could drive away. So the underbelly of Perseverance is actually higher than the topmost part of the Ingenuity helicopter. So it could drive away. Good ground clearance that. But there's no way to pick it back up. So it needs to follow along. And if it can never fly as a helicopter again, they may have to leave it behind. But right now, because of everything being shut down, because of the celestial alignment, they're both near each other, but they're not communicating for a different reason. But they found out enough about flying a helicopter on Mars that they now have the math to do it elsewhere. So they're thinking about other helicopter or airplane missions on Mars and on other moons of larger planets, but they haven't got any specific programs yet, but they're kind of queuing them up. But NASA's not the only one with things orbiting or on Mars. As was mentioned earlier, China's done an excellent job of getting an orbiter to Mars and then landing on Mars and then roving around on Mars. But there's also European Space Agency, Japan, Great Britain with its Beagle 2. Beagle 1 didn't do so well, but Beagle 2. But today we're
I like the idea last week of just flying the Ingenuity on top of the Perseverance rover.
well, I suggested that, but I took a look at a picture of the top of Perseverance. There's not enough open flat space for Ingenuity to have a margin of safety for sort of piggyback riding on Perseverance.
Oh, that's a shame. That's a good idea.
So look forward to the day when, if there's a failure of the helicopter mechanism, that Perseverance will just have to drive away and do other science and probably won't be coming back.
Oh.
I know, sad. I mean, the helicopter was a demonstrator, and it's demonstrated and gathered far more data than they ever anticipated. So it's been a definite success. So what is it that they've been doing? So the Perseverance rover has cameras, and it has a mast cam on top, so it can take stereoscopic 3D images. And the helicopter has been doing flyovers of areas where the rover is going to go, so it can plan out the autonomous roving of the rover. The rover, as we've seen, can take selfies of itself. And this is where it takes a bunch of images around 360 degrees, and then it stitches them all together and kind of subtracts the arm out that is holding the camera that's taking the pictures. So like, how did you get an overhead shot of the rover on Mars without the camera arm in the way? Gluing together images and subtracting out the bits you don't want to see. No, we don't have another flying rover. But I guess they could fly Ingenuity over the top of Perseverance and take pictures. I think they have one of those, just to prove they could do it. But it's flying at more than 15 feet above the rover, just to make sure nothing wrong happens, because the rover is expensive and you don't want anything wrong to happen. But the rover also takes stereoscopic images of open plains of Mars. And the idea of the stereoscopic images is it can determine the height of things. And another neat instrument aboard Perseverance is a gas separator. So one of the things we're going to have to do once we get to Mars with people is where are you getting your oxygen from? Well, if you have a place like Mars that has lots of carbon dioxide, if you can split the carbon dioxide up into carbon compounds and oxygen, you've got oxygen. And if you can do that by taking what scant amounts of water you have and putting it through a catalytic conversion, you can actually get water and oxygen from the CO2. And so that's basically what they did, was on a microscopic scale, just to prove they could do it, they have a little atmospheric gas separator that can produce oxygen and water vapor. Proof of concept, which NASA does on occasion, and this was another success. So they can do this, have something land on Mars that is purpose-built to be an atmospheric gas separator, oxygen generator, and water generator for future missions. So that would be very good, because then you don't have to bring it all with you, which reduces the weight of spacecraft. Another thing that Perseverance is doing, and we've seen this with its coring drill, is it can drill into rock and get rock samples and then put them inside of sealed cylinders for later pickup by the European Space Agency's recovery mission. So Perseverance will be leaving these rock breadcrumbs behind, and they will be logging the specific locations of them on Mars to go back and pick them up. I don't know that they've fully thought this out, unless there's some kind of solar powered or some other homing beacon, RFID homing beacon in these things. The return gatherer can get to the general location and find that, oh, it's buried under 20 feet of sifted sand. How are you going to get down through the sand? It's not just going to be sitting on the surface of Mars anymore. It's going to be buried. So it'll be
It's
interesting.
going to be planned like a cache. They're going to live in a specific place mapped already.
Yes, but
Hopefully it's going to work,
you
and
can get,
not one dune is going to cover it.
yes, you can give it X and Y coordinates, and you can have a Z coordinate that is the current surface of the sand on Mars. But if you get a drift of sand like Mars has sand dunes. And if you've seen them from the Mars Reconnaissance Orbiter, they actually go like waves of sand, and they get to be, 20 feet tall. Hopefully none of their samples will be buried under 20 feet. And if it is, maybe the return mission will have a little scoop. Maybe you can scoop some of the sand out of the way to get a few feet down. But we'll see. And the Ingenuity Helicopter, which takes images for future rover travel plans. So this is where it all stemmed from. This is where I got a lot of the information from, plus current news stories. So this is the NASA JPL day in the life story, and what Perseverance has shown them that they couldn't see before and what it might mean. So here's what's in their to be confirmed list. Mars had at one time far more water than was previously thought. There's a lot of postulation about Mars had oceans, and then it was, no, Mars only had lakes, and Mars was lucky for its water to have existed at all and then last for as long as it did. Well, once you start examining the rock formations and the sand formations, you learn that there was a lot more water on Mars than we originally thought. And the water lasted on Mars for more millions of years than we originally thought. And it took a much longer period of time for the water to be depleted and evaporated off into space. So it at the molecule level, it left Mars much slower than Mars's gravity should have allowed for it to do so, especially given its low atmospheric pressure. But the one that they recently discovered was, they've often said there's a lot of floodplains on Mars. And the only way you can get a floodplain, this is, imagine you have dirt in your yard, and you take a hose and you bring the stream of the water from the hose to about a 45-degree angle, and then you start like using the hose to move the dirt around to push the dirt. And it creates a microscopic version of a floodplain. And by looking at the floodplains on Mars, they had wondered, how did the water get moving this fast on a planet with such a low atmospheric pressure? And what they realized was, look at the craters. There were craters that were filled with large quantities of water that the crater sidewall broke away under the pressure of the water, or maybe those Mars quakes, maybe. But crater walls broke away and allowed large quantities of water to suddenly become rapid flow water, which created a lot of the floodplains. But all four of these bullet points are postulations based upon data observed, and they're going to have future missions go back and get similar data to confirm their postulations. But it's just kind of interesting that more water than we thought, lasted longer than we thought, depleted over a longer period of time, and actually was in huge moving quantities, which contributed to the creation of floodplains. And if you've seen the pictures of lava tubes on Mars, if there was a lava tube that opened up to the surface and then a crater wall broke open and the water from the crater found its way into the lava tube, then that would protect large quantities of water as subsurface on Mars. But since we've not been subsurface on Mars, we have no way of measuring it at the moment. So it'll be interesting to see what NASA does in the future with subsurface analysis of Mars' potential for water. There could be subsurface large quantities of water. Mars has a lot more information just waiting for us to discover it and go, I didn't know that. So this is the one we found out this week. If you've ever tried flying into or out of the Phoenix or Las Vegas areas here on Earth, and tried doing that when the temperature outside was above 110 degrees and had your flight postponed or canceled to another day, that's because if you want something to fly in the air has to be dense enough in order to support the aircraft. And they've realized that on Mars now. They always knew that the atmospheric pressure on Mars is far less than it is on Earth, which is why the Ingenuity helicopter had to have blades that were bigger, longer, tilted sharper, and rotated far faster. So they did that, and they were successful 13 times, 13 out of 13. But then they went to do the run-up on their 14th flight, and they were getting feedback data saying, not so fast. Well, if you've ever examined the upper mechanicalisms of the helicopter blades and how the helicopter blades can be tilted and how they tilt dynamically to increase and decrease the vertical thrust of the helicopter, you need that rapid tilt ability. And before the Ingenuity helicopter ever takes off, it does a spin-up test where it gets to very close to 100% of the propulsive force needed to lift the helicopter off, and then it shuts down. So it runs its speed, it runs its prop up, and it feathers it back and forth a little bit to see that it can do it, and then it shuts it down. And then they look at all the data, and if the data confirms it, then autonomously it can take off. And what it did on flight 14 was, okay, we're going to fly now. And autonomously it was given the order to, here's your mission, take off and go over here. And it went to do its powered up run up, and the servos for controlling the tilt of the rotor blades said, this is not working how I expected. I'm putting this much rotational force into it. And when I tilt the blades, the blades are essentially being jittery. They're not providing a sustained pressure. So the thrust of the bearings is saying, we're not getting the lift we expect under the continuous control that we're expecting. So autonomously, it shut down and said, hey, Earth Mother 1, I think we have a problem here. And then we got into the opposition, and we're not going to fix this until several weeks from now, when we can once again play with stuff. But I think what they're looking at is, I don't think it's just sheer durability of the mechanical bits, because I think they've done enough field trials on Earth, which has higher atmospheric pressure, and when you're rotating it even faster, if it's specifically where in atmosphere, that when the atmospheric pressure gets lower, that's not going to be your problem. I think the problem is there's ever-present glass-like dust particles in the atmosphere of Mars. And with the helicopter sort of blowing things up, circulating the air as it takes off and lands, I think what they've got is some of that microscopic glass is getting into the gearing mechanisms and the solenoids of the blade tilt. But that's just my guess. But we'll see in another few weeks after we come out of opposition.
I have a question because I'm not reading, I'm not following that much because I'm not doing outreach.
Yes.
So is Mars the area where the new rover is during the summer for them?
Given that the atmospheric pressure is being reduced, I've got to believe that the temperature is rising. That would say it's summer.
So then for me, my guess, my uneducated guess is maybe the lower pressure. And then because of the lower pressure, there is not enough lift.
Well, supposedly when they were doing their calculations, they had atmospheric pressure readings from a number of prior probes on Mars. So they kind of knew that it was going to be lower seasonally, but I think they took that into account in their servo design, how fast they had to spin up the prop. But we'll see in another few weeks. If they just have to go a little faster, I'm sure that the motor that they're using, the RPM of it, has an upper threshold based upon the amount of power they can put into it based upon the battery size and the solar panels. So if they just have to goose it a little more up to the maximum RPM of the motor, that may be a solution if it turns out that it's simply atmospheric pressure. Or maybe they can wait a few more weeks and see that the pressure has come back to normal, or see if they have a slightly cooler day. So they should be able to gather the data to determine if it's variations in the atmospheric pressure to the tolerances of the helicopter that they've built or something else.
Anyway, they complete the primary mission, they complete the secondary mission, and now it's just let's have fun and see what happens.
Roll them dice, yeah. Roll them bones, as they say. Yes, as a technological demonstrator, it is proof positive that you can fly things in lower atmospheric pressure. As a mechanism for overhead, higher resolution picture taking for where the rover is going to be in the future, yes, absolutely, it's been the pathfinder for Perseverance. So not only is original mission achieved and going to be useful in the future, but also something they cooked up along the way also turned out to be useful and to give it much more livelihood. So it'll be interesting to see, they haven't had a failure of the helicopter. All's been working well. The helicopter didn't try and take off and fall over on its side kind of thing. Or it didn't, break a blade or anything like that, because that would be very obviously noticeable. This is just, it's not performing to spec. It's not the sheer rotational speed that's the problem. It's the stability of the servos to rapidly tilt in a controlled and sustained manner the blades. So we're now in opposition. If you go to the Mars 2020, which is the Perseverance website, they actually have a video simulation of the alignment of Earth, the Sun, and Mars. And with the Earth at the center of the solar system, yes, it is. If you have the Earth on one side and it's closer to the Sun orbit than Mars is, and Mars orbiting farther out, and Mars gets to be on the far side of the Sun from the Earth's perspective, then this giant radio noise generating thing called the Sun gets in the way of successfully communicating. Now, as Mars goes behind the Sun from our perspective, the noise gets to be very intense and hard to receive. So at some point we have to give up on it. But when it goes directly behind the Sun, it's like, no, you're not giving nothing. So we have to wait a few weeks. Now, how could we solve this problem? How do we do that on Earth?
Relay?
Kind of. We have satellites that are in polar orbits in order to do relays to things that are on equatorial orbits. And if you ever wonder about that, how does NASA have all of its satellites talking to each other and talking to, manned orbiting things like TDRS, TDRS? This is a bunch of satellites that NASA has for thing-to-thing communications, and they're in orbits that are 90 degrees opposite one another, and they're not geostationary, but some are. The equatorial ones are, but they orbit the Earth at different inclinations so they can act as radio relays to one another. So if we were to put something in orbit around the sun at about a little bit larger than the Earth's orbit, then when a space probe went on the backside of the sun, and if Mars is our target, we could actually have a space probe that we could use as a relay from Earth up to the probe and then down to Mars with the sun in the middle. That would be fascinating.
Is the subspace network?
Yes, it's our Earth subspace network. But think about it for a moment. How big are the antennas on Earth to communicate with Mars with the probes that are there? 100+ meters across. So if you wanted to put a probe above the pole of the sun that could communicate both to Mars and back down to Earth, you would need 2 giant dish antennas that would be the better part of 100 meters in diameter.
I don't think that's feasible. I think it should be equatorial orbit, like in the L locations of the sun and other objects. Because then it's a shorter way to get there, because it's very hard for you to come out of the line of the solar system and go polar on the sun. It's a lot of energy. I don't think that's feasible. Like physics wouldn't allow that.
No,
Like
physics definitely would allow it, but you'd have to do a lot of gravity ever lengthening orbits around the sun.
Yeah, but how you do something that's out of the line? You cannot have gravity assist that you can come out in angle, unless if you do a gravity assist in some Kuiper objects that have like weird orbits, and then you go like eccentric until you get to tilt. But it would take years and years for you to get there. So I think if you do like L orbits and in different angles, you can do a relay from something that's behind of the sun.
So have we ever taken pictures of the poles of the sun?
No.
Never?
I
sure?
don't think so.
You sure?
No, I'm not sure. Now I'm not sure.
Okay. So if we did, what would that mean? That would mean that we can put things in polar orbit of the sun.
I don't know if it can polar.
Yeah.
That is a lot of energy for my.
No, it's not. No, it's not. You just take that big gravitational thing at the center and you orbit it a lot. So it doesn't take much energy to incline your orbit over a long period of time. But if you want to go orbit the sun pole to pole, you start out with a very long elliptical orbit of the sun, and then you just gradually tilt the inclination. With every loop, you just need a very small delta V, and eventually you will wind up in a vertical elongated orbit. And then all you have to do is just retro to squeeze the orbit down.
I don't know if that's possible. I really don't know. Polar orbit principle, because we can do that planetarily, but I don't know if the sun would allow that. Because you have to imagine the sun would allow it. Gravity. How you can come out of the well of gravity in a different angle? I don't.
How do you do it on Earth?
I really don't know.
How do you do it on Earth?
Well, we do gravity assist and we do like a lush, because we have enough energy to go off angle. But you have to imagine the sun is so big.
No, you count on it. You count on the mass of your opponent.
I have no idea, Monroe.
Okay,
I
okay.
really don't know.
Look at the BepoColombo probe, because it has a very long orbit of the sun. If you can do a long orbit of the sun, all you need is the inclinational slow incrementation, and you can take it over the pole. So there's something to research for next week, is
Okay.
solar polar orbiting.
Oh, I'm actually looking here. I haven't seen anything about the pole of the sun.
You know the guy that could actually answer that?
Oh,
Scott Manley, the guy that does
Okay.
all the YouTube videos about orbits and stuff.
that would be a good question to ask him. I love those sessions because we end up with questions that we don't even know the answer, and then we find like cool questions to ask for people who know what they are doing.
Or, Scott's done a lot of investigative research into it. You know that although he's an engineer, where he got all of his space smarts was from playing with the verbal space program software. That thing that simulates rockets and simulates orbits and stuff. He just, like playing a video game, he just learned orbits from that thing and all of the things that it doesn't pay attention to and what it allows you to change and how you can create unreal things. Like if you were building a traditional rocket, could you ever leave a super Earth? If you were a resident on a planet that is 1.5 times the diameter of Earth, could you ever create a chemical propulsion rocket system that would allow you to leave orbit of that planet?
I don't know. I don't think so. Depending on the mass, yeah.
It is very difficult to just get stuff into
Because
low
maybe
super
nuclear.
Earth orbit.
chemical, I don't think so, but nuclear, maybe.
Maybe, but then you're going to pollute your planet.
Yeah.
We're once again kind of lucky here on Earth that our chemical propulsion technology allows us to spend a lot of money, but we can create rockets that can go into deep space. Now with very heavy things, I mean, it's easy for us to launch a 10-ton satellite into geostationary orbit. We just use one big rocket and everything's disposable. But, maybe we can launch a couple of tons to Pluto, but it takes 10 years to get there. So it may be that there is a kind of a balance that if you're on a planet that is slightly smaller than Earth, you may actually develop a successful chemical rocket program sooner. If you're on a planet that is, 50% or greater in size and mass than Earth is, you may first develop exotic forms of propulsion and find that chemical won't get you anywhere. If you look at Goddard, when he first started playing with chemical rockets, he went through a lot of formulations before he discovered what could be energetic enough to actually get his rockets off the ground, because his rockets were made out of heavy metal. They weren't lightweight materials. So, it could be that if you're on a super Earth, you may give up on chemical propulsion entirely, and your first transits off your planet may be some exotic form of propulsion that we're just now thinking about. Like, I don't know, warp drive would be too exotic. It'd be completely unbelievable, I'm sure. But there may be forms of propulsion that we just haven't explored yet because it's been so easy for us to do with chemical rockets. Even ion propulsion, it's the same concept chemically. It's just, F equals ma. You take something, you throw it out the back, you go the other way. Everything that we've ever launched from Earth is based upon that.
Yes. It's just like if to go to a solar polar orbit, it would take a very long time. For what I understand, it would take a very long time, and would be like an expenditure of energy would be very high for you to get maybe a more linear orbit. but I haven't read. I have no idea if it's that possible.
We had the stereo satellites in orbit to do.
They're in the plane.
They're in the plane of the solar system, and they were at different L points, so they could do stereo angle on the sun. But they were in orbit around the sun at the Earth diameter orbital distance. So you can create an orbit around the sun at 90 million miles. So all you really need is the slow thrust to continuously tilt the orbit.
Yeah,
Or,
but then
Excuse me, Monroe,
yes,
Monroe, you keep talking about L points, and you might have mentioned what that was, but I don't know what that is.
oh, okay.
Okay, so if you imagine that the planet or have you seen the experiment that I did in the observatory where I put a fabric and I put weights and I create like bumps on a fabric? So those bumps, are like, imagine two heavy objects that make bumps. So in those bumps, that areas, they're flat. In those flat areas, you can place spacecraft, and you don't even to have any expenditure of energy. It's like it's free there because you don't have to planet moving. It moves together with the orbit because those equilibrium points are moving together with those two bodies, those two objects. So in that case, we call it the L points, the Lagrange points. So that will be a flat areas in space-time where you can place spacecraft or planets or asteroids, and they keep following the same orbit. The L points in Jupiter are full of asteroids because they are kind of in the area that's flat, and they keep like just following. Monroe is showing you the L points.
Okay, my deeper than most knowledge of the L points comes from my working with the James Webb Space Telescope, because the Webb will be in a halo orbit at L2. So this picture shows you the Earth going around the sun, and there are multiple of these gravitational stability points. It takes a lot of energy to get to them, but once you are at them, you can kind of hang back and not do much. But the solar wind will still push on you. So you won't stay at precisely the same place along the orbit. You will actually slip forward and backward along the orbit. And Trojan asteroids are debris that winds up in these pockets of L4, L5, L3. And they tend to stay there, but there's a whole class of transitional asteroids whenever you have a large body like the Earth or greater in size, where they actually have orbits that go from, the center of L4 towards L3, back to L4, and then back again. So they cycle back and forth in these orbits. They're still considered to be in an L station, but their station is forward and back. So they go back and forth in the orbit. L2 is a lovely place in the Earth-Sun orbit that you can hide in the shadow of the Earth. You can hide, for the most part, probably 18 out of 29 days, you can have the moon on the other side of the Earth. So if you want to look the other direction, out in deep space, this is a good place to hide. So the Webb will be sitting at the L2 point.
Monroe,
Yes.
I place a GIF for explaining the Lagrangian points with the bending on space-time. That picture that I wanted to print in 3D.
I have a question.
Yes.
Is this an orbit? This L or 4 or L5? Is that an orbit that they're in?
Yes.
They're not so much orbits themselves as they are stable points in the orbit of a multi-body system. So if you have the Earth going around the sun, there are places you can hang out in the Earth-Sun orbit that allows you to have a free coast You don't have to continually fire your rockets to stay there. So there's kind of a stable place. But if you look at the use of L2, L2 itself is not entirely stable. L2 is on the edge of stability. So if, let's see if can I stop this?
And maybe that is a picture. Let me see if I
It-
find the
it-
picture.
Is there some other letter that they use for an orbit besides L?
No, it's because
It's
the
named
person
after the
who
guy that came
calculate
up
the
with these
math is
orbits.
Lagrange.
Yes, it's named
I
after a
didn't
guy
get
that
that.
came up with these orbits.
Yeah,
Oh,
so
okay.
those orbits are, imagine that if you make a solid object of those orbits. So those bumps are the well of gravity of the Earth and the well of gravity of the sun. So when you have those, you imagine like you put your finger on the jelly or some tissue. So as you press it, there are points, they're flat. So if I throw sand in that picture, and you could see that the sand would accumulate in those points are the Lagrange points. Because that, as you can see in space-time, they don't curve down, they don't curve up, they're kind of flat. And that's where in space-time you can keep spacecraft in there, or asteroids are stuck in there in the case of Jupiter and Saturn. So even Earth has some asteroids, they're stuck in the Lagrange points of Earth, and that's the perfect place to get satellites. They're far away from Earth on the sun. In that same page, you might find the Lagrange points in picture instead to be the, oh, so let me see okay, I have a better picture here. I'm gonna send you the link. This is the same one, Control C. Okay,
Look at what
I'm
I
gonna
got.
send you the picture. Oh, okay. I have a
Just me.
biggie. Okay, I'm gonna send, okay, go and click the last link.
Hang on.
And you're gonna find the biggie one with a little bit more detail. Okay, so as you can see, now it's not rotating. So you imagine that the sun is heavy enough to bend space-time and make a huge cone. Same thing for Earth. Earth has less mass and makes a smaller bend. Now, if you see the top areas where you have this bend, those areas are flat. So imagine that if I throw sand in this object, this physical object, the sand would accumulate where those places there are flat. And by coincidence, those places that space-time is flat is where you accumulate asteroids and where you can place spacecraft. The mathematician who discovered that by math, not actually observing, this was before even the theory of relativity for us to understand that space-time could be represented in 3D. He calculated those areas, and those Lagrange points are the area of stability. So you can place asteroids, or you can place satellites. So let's say L2. If you look at L2, where James Webb is and where all the satellites that we place there, all the telescopes, in that area, as Earth orbits the sun, that spacecraft can orbit the sun too in an outside orbit. And as it does, it can maps the whole of the solar system in the nighttime of the Earth. So it's protected by the radiation of the sun. It's has like a shield that protects itself and gets the very cold space where it can measure with more detail and less noise. So it is just a perfect orbit to place telescopes as L2, because you have a free ride where you can orbit the whole solar system without having spacecraft combustibles or any spacecraft, material to actually push you in the orbit, because planet Earth is actually doing that by the well of gravity. And the same thing are for the Trojan asteroids in Jupiter and Saturn on Earth. So it's like a free orbit because there is no energy being expended there, and you can actually orbit the sun in those L orbits. That's what we call it, the Lagrange points.
All the L's have this ability, all the L points.
Yes,
have this ability.
every one of these 5 points, whenever you have two large body gravitational masses, you'll have these. So Jupiter, Saturn, Uranus, Neptune, they all have these 5 L points. So, we use them for convenience. When we did the stereo sun observing probes, we put one of them at L4 and one of them at L5, and they could take images of the same spot of the sun at 2 angles and create stereo images of it. The problem is solar radiation pushed on the spacecraft, so they did have to expend fuel to stay precisely at their L4 and L5 points. And when they ran out of their fixed fuel supply, they drifted. So the one that was at L4 went around to L3, and the one that was at L5 drifted backwards to L3. And as they both wind up at L3, you have the opposition problem. So we couldn't communicate with them. The one that went through L4 past L3 and then back around is now back around on the other side. That's one of the, I think that's stereo B. The other one we lost because it drifted around behind the sun and we never saw it again coming out the other side. Now I'm sure it's still there. We just don't know where to point the antennas to talk to it, and it doesn't have a transmitter powerful enough to talk to us. So we've used the L points for a long time as free ride locations. Now, we don't use L2 in exactly the same way as we use L4 and L5. If you were to think of L2, it's a point. It's not really a wide area. If you look at the L4 and L5 in this 3-dimensional picture, you see these large purple swirls underneath it. So L4 and L5 have a wide variability. You can play off of the L4, L5 and still have a stable place. Look at L2 and L3 and L1. They're very narrow points. They don't have a lot of curved space to play with. So if you want to be in orbit of L2, you can't just hang out at one location because then you're hogging it for everybody else. Nobody else can do it. And the Spitzer Space Telescope, which we've shut down since then, the Spitzer Space Telescope is hanging out back in Earth orbit, and we moved it out of L2 because we have the James Webb Space Telescope that wants to be in L2. There's
And
another
Kepler's
thing.
still there.
There's another thing. The Russians also have a radio telescope that's at L2. So you can't all be at L2 at the same time. You consume a little bit of energy, and what you do is a halo orbit of L2. So L2, there's no planet at L2. How do you orbit something where there's no center? Well, you use thrust to give yourself motion in one direction, and you use the solar wind to push you from the other direction. So it's a push-pull halo orbit. So if you ever read up about James Webb, you'll find that the James Webb Space Telescope is not precisely at L2. It is in a halo orbit of L2, and that consumes fuel. So it has a maximum lifetime of about 10 years, which is their calculated propulsion lifespan for their hydrazine fixed fuel supply.
And
Imagine-
also the cooling for the taking infrared pictures.
No. 5 years is the life of the helium supply. 10 years is the life of the hydrazine propulsion supply. So much like Spitzer had 5 years of cooled imagery in a stable orbit at L2, the Spitzer ran out of helium first, but still had the hydrazine to keep a stable orbit. So you had a cold and a warm 5 years. But at the end of 10 years, it did not have enough hydrazine fuel to stabilize its halo orbit at L2, and they had to move it out of the L2 halo orbit. And the
Mauro,
Webb
you
is
need
going to
to
go through
figure
the
out
same
the
thing.
way to do that object in 3D.
Do what object?
This, I want this in printed in 3D.
You just have to learn CAD. Computer aided design, draw it in 3D. So anyway, these are the L points. And the Webb will be orbiting the L2 in a halo orbit. And stereo A and B, we're at L5 and L4. And why would you not want to put anything at L3? Because the sun would always be in the way.
To communicate.
Yeah, so then you need your polar orbiting object. So we've been assigned a subject matter expert. His name is William, but he likes to be called Will. And I sent a question to Will and said, okay, if the Webb is orbiting in a halo orbit at L2, and in order to keep its instruments always cool, there's the solar shade on the bottom. So is there a 3D model of the viewing perspective of the Webb? He hasn't gotten back to me yet, but apparently it's a question he'd never been asked. Think of it this way. If I take the solar shield of the Webb, I have my model. This would be interesting. We can actually use it as a real model now. So if the Earth is here and the Webb is here at L2, and you can see how it's got its sunshade on the bottom so that the sunlight doesn't hit the instruments on the front. So,
excuse me, is it just me, or does everybody see that you are frozen? Your video is frozen, or is it just my machine that's?
No, I
frozen?
can see him moving. He's
I
not
can
He's
see
frozen.
you
moving.
moving.
All right, then it's me. Okay.
no, it's not you. I'm not showing my camera. You have to look for me in the list of people's cameras.
Oh, yeah.
Now you see it
No,
moving?
you can, are you going to still show more stuff? Because then you can switch and show the model.
I will switch my video. Give me a second here. Ta-da! Is that any better?
Yes, but you can switch like for a full screen. Maybe that is what I can do in my own view.
I think that's what you can do. I can't make me any bigger. I'd have to get closer to the camera.
Okay.
So
Yeah.
remember the L2, you've got the sun, and then you've got the Earth, and then you've got the James Webb Space Telescope out at L2. Let's turn it around this way. So this is the Webb at L2. Here's the sunlight hitting the bottom. We never want to do this because that will destroy the instruments. So we can't do this. That would destroy the instruments. So it's always got to be like this. And given that it's like this, it can rotate this way. Now the instrument can't actually rotate on top of the sun shield. They use their momentum wheel and they actually orient the spacecraft this way. So think of a 3D model. If I can rotate this way in 360 degrees, and I cannot do this or this or this or this, because then it would expose my instruments to sunlight, and I'm on the Earth L2, so I'm swinging around in the orbit of the solar system, it creates this three-dimensional lobe of what I can see at any point in time. So if I want to see something that is over that way, I have to wait until the Earth orbit puts me in that direction. And now I can rotate around and see in that direction. So it's a non-trivial mathematical 3D model to say, what are the viewing possibilities of the Webb at any particular point during an Earth year?
By the way, you
sounds like
should
a
post your
very-
picture on the web page that you have your model. Did you 3D printed that one?
Where have you been? Oh yeah, that's right, you were on the road. Yeah,
Yes.
this is my built from scratch 3D model of the Webb.
Oh, it does it fold?
Yeah, I actually wrote the open SCAD algorithms for doing this, and then I printed it in multiple colors based upon the image of the James Webb Space Telescope. Now, you want to see the coolest part?
Yes. Oh, that is so freaking cool.
You like
Does
that?
does the secondary folds too, or it just stays like that?
No, that's the secondary's fixed.
Okay, but no, just that is already super awesome. And I
Yeah.
like that the printed plates are curved like they were, you know, made of thin material, but that they it's looking so good.
Okay,
Now, I have
let's
a
see. Let's see.
question.
Yes, Joanne.
It seems like an awfully fragile equipment that it will get damaged so easily out there if it turns so many different ways it can't move without
Yes.
being
Let me tell
destroyed.
you something.
It
There will
is.
be a bunch of people here on Earth that will be a month without breathing.
It will
Because
take,
just to unfold the telescope is going
Yes.
to take a whole month.
from launch point on Earth until it gets to its halo orbit with everything unfurled and assembled takes a little more than 30 days. And things like these 5 layers of mylar are incredibly thin, and they do curve like that. So the telescope is actually sitting in a dimple in the mylar. And these things on the outer edge, those are actually the cleats that are actually wound up to the telescope. And this stuff that's on the bottom, here's the solar panel. These are thermal radiators. They all extend and unfurl. And these are the 2 support rods that pull the mylar film out to the edge. Everything must work perfectly. On the back, I do this with great detail here. This little guy right here, this is a folding thermal radiator. The electronics produce heat, even though the actual sensors are in liquid helium inside this box. The electronics produce heat, and to get rid of the heat in space, you have this little triangular with a gap through it radiator that will
That's
radiate the heat from the
beautiful.
instruments. Otherwise, the instruments won't work. Now, if it's at L2, I'm giving away far too much. I should make you wait until December. If it's pointed like this or like this, if you want to point it up, which way is up in space? Think of it this way. Which way is Earth? Earth is that way, always. So where's the antenna? Here's the antenna. There's an S band and a C band antenna. So I even put the antennas in there.
It's
So
beautiful.
if people
it's really
go,
beautiful.
if people go, well, how do you communicate with Earth?
Yeah,
Using
the
its
high
2
gain
antennas.
antenna and the AM antenna.
How long has it been up there now?
Not yet.
Not at
It's
all. It
still in the
hasn't launched yet.
Caribbean.
It hasn't
It
launched
hasn't been
yet.
launched yet.
It's more
How
than
many
10
people
years
believe that
behind
it's
on its
gonna-
launch.
Did
And
didn't
how long is
it
it gonna be up there
left
for?
the continent? Did it arrive in the Guyana already?
No, it's not in Guyana yet. I would suspect that it's either about to start its trip to Guyana or it's going to be doing its trip to Guyana, because towards the end of October, there is a news media event in Guyana that journalists have already been invited to. So I'm thinking it's either already left California or it's on its way. Oh, not California, Maryland. It's at Goddard.
How long is
Yeah,
it supposed
so
to stay up there
during
for?
the whole traveling, a lot of scientists who, you know, develop and are going to work and get the data, they are already not breathing because the thing is in the ocean.
Yes. They didn't want to communicate when it was going to be the open seas because pirates may capture the ship. And, you know, somebody said, why doesn't the US Navy offer a flotilla? And I said, well, NASA is a division of the Department of Defense. And yeah, they could definitely justify for the billion-dollar James Webb Telescope, spending $20 million to have a couple of Navy frigates escort it. But we shall see.
This is a because he already has a telescope out there. This is a new one.
Yes, this is a new one. We did have an infrared telescope out there called the Spitzer Space Telescope. It is smaller, much smaller. It doesn't have all these solar shields, and it's just not fancy and contemporary. Spitzer's like 20 years old design. This is only about a 12-year-old design.
Is it as fragile?
Describe fragile in the vacuum of space.
Well, you say you can get it damaged if it turns one side or the other side.
Yes, from the heat of the sun. The electronics are very sensitive to the heat of the sun. So the heat of the sun can destroy the instruments if it, accidentally pointed at the sun. So you don't want that.
Yeah.
Yeah.
We all our
Let's say it
equipment
was
that goes up here is
engineered to
fragile?
survive that.
Yes.
It's just a lot of moving pieces, but it was engineered to survive that. And then you have to imagine this is a huge telescope, and they had to use the origami technique to actually
Yes.
fold and fit inside of the spacecraft. So because of that, we'll have lots and lots of the tiny small parts. They're movable, like the Spitzer telescope was very tiny, so you could fit in the whole spacecraft without having folding or having any technique. In the case of the James Webb, it's a huge telescope. It's like 3 times as big as the Hubble Space Telescope. So that does not fit in a small spacecraft. So you need to fold the whole thing to actually fit in the spacecraft. So what they are really afraid is that some of those servers, some of those milers, some little thing comes out wrong, you lose the mission. But they trained it out, they tested, they did it, and they're ready. So it was, let's say that from trying out and fixing problems and probably they took 10 years just for that. They had already the mission ready. They have all the funding, they have all the things, but because there was tiny little technical problems of everywhere, that's why it took so long, because there's a lot of moving parts.
Okay, to give you an idea of the size, this rhombus, if you look at this pink sort of slanted rectangular area, which it's really like that, that is the size of a tennis court. So if you were to say, how big is the bottom surface area of the James Webb Space Telescope? It's the size of a tennis court. That won't fit inside of a rocket. So it all had to fold up, including the mirror itself was too large in diameter to fit inside the fairing of the spacecraft that's going to launch it. So the mirrors actually fold backwards like that.
And
Just
the
enough to get it to
secondary
tuck in.
folds to be flushed to the telescope.
Yeah, they'll actually have to open themselves up. Now they're not actually flat, they're curved. It's kind of difficult to make it out on this, but I actually printed it in 3D as a curved shape.
It's like a makeup mirror.
Yes, concave. Here's my favorite part of the James Webb Space Telescope. See this little black thing right here?
You
know what that is?
No.
The Webb Space Telescope will use that for solar wind propulsion.
Really? To stabilize the orbit. That is cool.
Yes. So remember me saying it's going to be in the L2, but it's not at a spot. It's actually going to be orbiting L2. And that for
it probably
some,
needs to rotate because
yes,
it needs to take picture of the whole sky. So
for
not just
some-
going up and down, it needs to
Yes.
actually rotate in itself too.
yes, it needs to rotate like this as well. It rotates like that. That's normal. The telescope itself doesn't turn within the solar shield. That would just be too complex. So the telescope is mounted into the solar shield, and it's in a L2 orbit. So it's doing a halo orbit like that. Now, 50% of the time, it needs to use its rocket thrusters to kick it up to the top of the orbit. But when it wants to come back down to the bottom part of the orbit, it just rotates itself like that, and it flips this flap into the sun, and it lets the reflection pressure, the solar sail of the sun, push it back down.
Photonic propulsion. That's awesome.
That stuff doesn't exist. Now, I don't want to hear it. No, 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 no. NASA's already using a solar sail as a propulsion mechanism
That's
on the
really
James
awesome.
Webb Space Telescope. So
That's
obviously,
really awesome.
I had to print that in black because that's actually what color it is. Now, why is it black? Shouldn't mirrors reflect things?
It's
No,
absorbing
what they wanted to do is have the panel, which are made out of flat aluminum. They wanted the panels to absorb as much of the sunlight as possible because it's not actually the reflection that is generating the force. It's the infrared heat coming off of it.
And the few
So-
molecules of the solar wind will move the telescope.
But how can you do that in the vacuum of space?
Not quite vacuum, it's close to vacuum.
Exactly. It's not quite a vacuum of space. There's enough molecules left over that it will actually be using it for propulsion.
This is really awesome. This is really a beautiful model.
I
I
like
loved it.
and if
The-
anybody,
you know what it needs to be?
What?
Painted silver for the mylar. Or silver or it's gold?
oh no, they're not silver. The
The-
Webb
it-
Mylar is not silver.
No, it's gold?
It's not even gold. It's purple.
Oh, really? Okay.
No, it's purple because the Mylar is so thin that you get a chroma effect off the Mylar. So if you ever,
Oh,
if you look at the pictures of the Webb, when it gets fully deployed in space, the bottom side will be this pinkish color and all of the layers above it will be kind of purplish.
Oh,
So
okay.
all of the things meant to reflect sunlight are purple. All of the things that are meant to reflect infrared heat are black. And the infrared mirrors are all beryllium metal.
Gold.
They're little thin discs of beryllium. So they're golden color, but they're not gold. They're beryllium.
That's
little coin.
beautiful. That's really beautiful.
Okay, since you
I
didn't
loved it.
since you didn't see it, I guess you didn't recognize it, but how about that?
Oh, that's the holder. Oh,
This is
that's
the stand
awesome.
for it.
That is really beautiful. OMG. We need to go to a fair and have put that like to show off.
Well, I'm going to show it during the presentation, and the presentation is obviously going to be recorded so that NASA can make free use of it if they want to.
Okay.
I've already mentioned to my minders and to Will that I've got the 3D model. If you want NASA to play with the 3D model, you can. But as a compromise, in case it didn't come out right, ta-da! I took their paper model and printed it and assembled it.
Oh, okay. That's cool. That's cool.
So it's kind of not bad. You print it on a color inkjet printer, and then after about 4 hours worth of X-Acto knife work, you get this.
Yeah, you make people look at your model. If they want to hold something, they hold that.
That
Exactly.
doesn't look so fragile as your model makes
Really?
it, which I
Really?
realize it looks. Yeah,
Look at the
this one
secondary.
looks-
Look at that. It's all
No, I'm
wiggly.
not talking, but I'm talking about the middle part there.
Yeah,
I mean, you
this
have
is
that on the
hollow.
other part too, but it looks like it's solid there, and it's not.
Oh, it's not solid. It's actually hollow paper. So there's a top and
And-
bottom sheet, and you bend it down and glue it together to make this shape.
Yeah, and I'm just saying that they presented that when they were going to Congress to get the money, it wouldn't look so fragile. I mean, I wouldn't want to send something up into space thinking that it's gonna not make it. How long is it gonna be out there for?
Well, when
It's
you're
going to be up there for
explaining
10
something-
years.
So when you explain something to politicians, you don't go into much detail. You just like explain how good it's gonna be, how many jobs you're gonna offer, and how many possible Nobel Prize could come out of it, and that's it. And then you zip about those fragilities.
Yes, it'd have to, because that I don't think there's anything else in space that has that many possibilities to be destroyed so quickly.
Oh, everything. The
Well,
space station is all the time.
it's not just the fragility of it, it's also the mechanical reliability of it.
Okay.
So it has all these moving parts, and 100% of them have to work absolutely flawlessly. Otherwise, it could scratch the whole mission.
Right. I
And
keep
then
hearing
the whole-
that. So
yeah,
how
and
did
the other
anybody
problems-
convince anybody to do that?
And the other problem is that the Hubble Space Telescope's right here. It's neighborhood.
Yeah.
So we could go travel to fix it when we have the space shuttle.
Oh, we can. Oh, well, that's a different
So we
story.
could
No, no,
fix
no,
it
no. When
Like-
we had the space shuttle,
when
Oh,
we
we-
could
okay.
service Hubble. We will be
Oh, okay.
unable to, with our current technology, service the Webb out at L2.
even if we had it, a space shuttle, we could not go because it's too far away. Imagine that's like
It would have
very
to be,
much far away than the distance from Earth and the Moon. So
It would
this is
have to
very
be
far
a-
away.
it would have to be an autonomous robotic spacecraft that would not attempt to repair the Webb out there. The Webb, strange as it sounds, actually has a grapple post on it. So even though they knew we didn't have a shuttle, even though we have no current technology for getting out there with manned craft to service it, they still went ahead and put the post on the Webb for grabbing the instrument.
Just in case.
Well, you
Just
never know.
in
But-
case.
But do we have, I mean, where it's going to be at, it's going to be so hot. Could we have anything go out there?
It is not anywhere. Remember, it's beyond the orbit of the Earth. So when you speak of hot, it's hot from the perspective of infrared sensitive instruments. As far as temperature goes, it's not that hot.
It's freezing
It's
for a human.
well sub-zero out there.
Well, it has you mentioned the rays that it had, and they're not good for people.
Well, I mean, solar radiation has a lot of X-rays in it, and that's not good for people. But it would not surprise me to find that before the Webb actually goes through its 10-year lifespan, that SpaceX is probably going to receive a contract to send a robotic probe out to it
Okay.
to grab it and bring it back.
Oh, interesting.
I think that's going to happen.
That would be awesome if we could save it, because that's the first like big important telescope.
That's what I'm thinking too. I think we spent a heck of a lot of money on it.
But
Yeah.
but
It has
it's-
to work
but
perfectly.
But just
to
think
get it to
about
work.
it. How are you gonna go to the Congress and say, we want $3 billion to save the Hubble telescope? They
Well,
will
to
not
save the
give
Webb
it.
telescope.
Yeah. No, I mean, save the Webb telescope. It's not. I don't think it would work. I was thinking about the Hubble Space Telescope.
Oh, they've already written off Hubble because NASA went to Congress and said, Hubble has ultimately a limited lifespan. You know, its gyros are going to go, its electronics are going to fail, it's going to run out of hydrazine for orbital positioning. Eventually, we're just going to burn it up. And I'm sure there were a few in Congress who went, hey, my friends over in the We Build Satellites business, is that a problem? And they went, no, boss, no, not at all. So they've already written off the Hubble Space Telescope, and there are a lot of people that would just breathe a sigh of relief when they have to burn it up. But in order to keep the money flow going, we have the James Webb Space Telescope, and it's going to go out there and be out there for 10 years. Is that all that NASA's doing? No. There's another space telescope that will also be infrared. It's called the JWST. That's the James Webb Space Telescope. What about the one that follows it? What's the next one? That's WFIRST, WFIRST, which is
And
now called,
during
which is
this
now,
whole time, that is Sophia. Because Sophia
Well,
has more 15 years of work service.
during the whole time that we're pushing with Congress to get money for the Webb Space Telescope, the Nancy Grace Roman Space Telescope, formerly known as WFIRST, is also being budgeted to get out there. So where's WFIRST going to be? Oh, it's going to be at L2. Well, what about the Webb? By the time we get the Nancy Grace Roman telescope out there, Webb will be old hat, and we'll, park it where we park the Spitzer. So there's always got to be a 5-year plan, because it takes 10 years to get these missions actually
Or
out.
20 in the case of the Webb.
Yes. Now, beyond the Nancy Grace Roman, there are actually 2 more deep space telescopes that are in the works. One is bigger than the James Webb, but not enormously bigger. And then there's one that's even bigger than that. That is, oh my God, that's as big as the biggest telescopes on Earth. And that one's for like 20 years from now.
There's a few ideas of constructing the telescope in space.
Yes.
Then you can make as big as you want.
So they're counting upon new propulsion technology and new kind of spacecraft like Starship from SpaceX to put bigger and bigger things up there. Now, the Webb, being infrared only, might be able to image an exoplanet as being something spherical. It might also be able to detect gases in the atmosphere of exoplanets, so long as they fit within the infrared spectrum. Not the WFIRST, the Nancy Grace Roman, and not the first of the next generation big telescopes, but the second one. That one is going to have full spectral imaging. So it's going to be able to do infrared, visual, and ultraviolet. It's kind of going to be like a super Hubble. It is going to be so large that they say for the stars that are within, I think, 20 light years or closer, you'll actually be able to image the atmospheres of those planets. That's how big that telescope will be. So look forward to things getting bigger.
Let's hope James Webb gets there first.
Well, you know what they say about nuclear fusion, right? Fusion reactor, fusion energy. They say it's 30 years in the future and always will be.
No,
Well,
and now the number is smaller.
10
Now
years in the future.
No, it's smaller than that. I think it's about 6 years in the future.
Oh,
It got better. It got better. Remember the hologram they are constructing that's a bit almost the size of CERN. They are constructing somewhere in Germany, I think.
France. It's in France.
Okay, yeah.
Yeah.
That will be a nice lecture to show that one to see, because the last time we looked, yeah.
I forget what its name is.
Hologram.
No. ITER, ITER. That's the name of the fusion engine they're building, is ITER, and it's multinational. The U.S. actually provided one of these 6 enormous magnets. It takes 5 of these enormous magnets plus a spare, so you can't leave any money on the table when you're talking to industrial engineering. So there's 6 total. The U.S. built one of them. So it'll be interesting to see what other nations build the other 5, and if they all fit together, because it's a giant tower. So the 5 magnetic rings have to fit together to create the chamber.
Yeah, I was only mentioning it because like the Webb Space Telescope is taking longer and longer in the future. That was the only reason I was mentioning that they say that about practical nuclear fusion energy. But I think I was reading in respect to that anyway, that the optimistic information that comes out of it about the things that you read now and then, saying that now we get 0.7% of the energy out that we put in to it and so forth, only reflect the amount of energy put into the plasma and don't reflect the energy put into the magnets, for example. And so that there really are huge hurdles still there that it'll take a while.
Yes, there's two Achilles heels that they have right now. One is the duration of sustaining it is still infinitesimally small portions of 1 second before it falls apart. And the second thing is they have yet to get more energy out than they are putting in.
And that is one more
huge quantity.
detail too. Control of neutrino radiation.
No, the neutrinos they don't care so much about. Neutron radiation.
Oh, neutron.
Yeah,
radiation.
I mean, it will be producing neutrinos, but they go through us all the time, so they're not worried about those. But the neutron radiation damage to the actual metallic walls of the magnetic bottle, that's going to be a problem. It's kind of like our fission reactors right now. You put the uranium into the reactor, you turn it on, and it goes for a year or two. And then you've got to take those rods out and put in some new rods, and then the old rods become radioactive waste for the next, 10,000 years. Well, when we finally get a fusion reactor going and we can get more energy out than we're putting in, that's wonderful. But they're estimating that the reactor walls will only last about a year before they have to be replaced due to neutron damage.
But at least they will not have waste that's going to be contaminated for.
Right. The neutron damage will be microscopically porous heavy metals, which won't be radioactive, but they will be, unless you're going to melt them down, useless for anything else. And we have to build a new one. How much is it going to cost to build that new chamber? And then how much is it going to cost to actually assemble it? Because we have to disassemble your reactor to do it. So if you want continuous electrical generation, you have to have at least 2 of these babies.
Hey, job stability in Europe.
What about this guy that has all those satellites up there? Like the first one must have cost him an arm and a leg, but the other ones must have come down in price as they found out, how to build them better and how to,
yes,
how it was going to go and how they would get up there. Is that true? That's my assumption.
But then he adds new capabilities to the satellites. Like every one of the satellites has 5 laser beams now.
Why does it need laser beams?
Because you can communicate from satellite to satellite using the laser beams, and you don't have to go up to the satellite, down to the Earth, go over the curvature of the Earth to some destination data center. You can actually go up to the satellite and then straight line over to the other satellite and then down to the data center.
So you're saying that even though you beat it up, is that you get it better, it's going to cost you more.
One at a time, right? So the lasers do make the satellite cost more, but it's incremental.
So what I'm saying is that the coherent communication loses less data. So that is less noise when you intercommunicate with lasers. And now the price of the lasers are ridiculous. It's like cents for the diodes.
Well, the lasers that they are using can communicate satellite to satellite at the gigabit level. So if you think about, if from my house up to the satellite, I can communicate at up to 150 megabits per second. And then I can communicate from the satellite back down to some local data center at 150 megabits per second. That's probably good. But if I have to go up to the satellite, back down to a local internet access switching center, and then I have to go over ground fiber, ground level fiber, which goes with the curvature of the Earth through some number of switches to get to the destination data center. That's a lot of speed of light travel, but it's even more data switching time. So if I can go up the satellite to satellite via laser at gigabit level, and then down at 150 megabits to a satellite station at the data center, I've probably knocked 100 plus milliseconds off of every one of my packet transmissions. And that's really what they're trying to achieve, is you can do this from space anywhere on the planet, and the end-to-end transfer time will always be faster than any point on Earth to any point on Earth, because you're skipping the curve. Now, I think the new satellites with the lasers might actually weigh a little bit more than the previous generation satellites that don't have the lasers, because instead of launching 60 satellites on one Falcon 9 rocket, they launched 50 satellites on one Falcon 9 rocket. So that it's not the size, because the incremental thickness of the satellites is not going to be changed that much by adding around the outside edge 5 lasers. But what is going to change is the total mass of the satellite. The satellite itself has a surface area of about a ping pong table. So if you think of the size of a ping pong table, if you stacked 3 ping pong tables on top of one another, that would be the height, the thickness of the satellite. So it's about the square area of a ping pong table at a height of about 3 ping pong tables. They're not big. That's how you can get 60 of them in the rocket. But that's on a Falcon 9. Starship, the next big generation launch vehicle from SpaceX, can launch 300 of them at a time. So if you think of the current number of satellites that SpaceX has in orbit is about 1,200. With 4 launches of Starship, they can completely replace with next generation all the existing satellites that are up there. And once they have that ability, if they find something that will make it go faster, reduce some delays, make operational costs less, they'll just do it, 3, 4 more launches, replace the entire armada. So anyway,
Nice meteor shower.
No, they are designed to burn up quickly and without any large parts making it down to Earth.
Yeah, but it's gonna be like a full of sprinkly thingies, the orbit.
They've already burned up 15 of them and nobody even noticed. There's 15 of them they've already decommissioned or deorbited or burnt up. Nobody knows. Back to Mars. So Perseverance is the largest rover for mankind to ever have roam around on Mars. Ingenuity was the first helicopter. Mars is wetter than they thought it once was. Mars water lasted longer, and the volcanism probably indicates why the craters sort of broke apart and released lots of water. And flying a helicopter on Mars in the summertime is non-trivial. And for about every few weeks, every 2 years, we lose contact with everything on Mars. And given how many billions of dollars we have on Mars at the moment, maybe putting a polar orbiting satellite for relay communications might be something NASA would be interested in. Any other questions about Mars, what we've got at Mars, how things are at Mars, what we're finding out about Mars?